All right. Hi, everyone. So I'm Leo. I'm a solutions architect at Amazon Web Services. And I'm going to talk to you today about two different small teams that used AWS to get really big results. So the first thing I'm going to talk to you about is NASA JPL and about the landing of the Mars Curiosity rover. And so they basically needed to live stream the whole landing, and they did it on AWS. And then I'm going to talk about Obama for America, which ran basically everything on AWS. And so I used to work at Obama for America. So I now work for AWS from 2009 to the end of last year. So I worked at the Democratic National Committee. And then as the Obama campaign started, I was embedded there, and I spent most of my time there. And just a disclaimer that, so Amazon Web Services doesn't endorse any political candidates. So I'm just talking about the campaign part, about my experience there. And also, that's a picture of me hugging the president. I think I'm wearing the same hoodie. So let's talk about NASA. So they wanted to live stream this Mars rover landing. And basically, they were expecting about 1 million viewers. It had to work on all kinds of devices, so iOS and Android and Flash and everything. And it was an HD stream. It was 1080p. And there's no room for failure, right? This was a historic moment. It couldn't crash. So now, there's some challenges involved. And so the first thing was that NASA has a regular live stream setup, and they told JPL, oh, you can't use that. And they told them that 6 days before the landing. Now, this rover had been on the way to Mars for 2.5 years, and so and then 6 days beforehand, they realized they needed a live streaming solution really fast. And it's also the same week as the Olympics. And so if you know anything about how people watch the Olympics online, basically every CDN was fully at capacity that week, so they couldn't really use CloudFront. They couldn't find a CDN to use, and they also only had 2 technical resources to make this work. So, and they decided they had to basically build their own CDN to live stream this, right? Now, the challenging part about doing a live stream setup is that, so you've got this HD video stream file, and so it gets added up in segments of 4 megabytes, and it never changes, and it's cacheable, so that part's easy. But the manifest file, which tells the player what video file to point to, that's only 4 kilobytes, and it changes every 4 seconds, and so you can't cache that. And just to be clear, though, so the streaming was it wasn't the actual video from the rover, because there's some latency involved with that and low bandwidth, going from Mars, and we don't have a region on Mars yet. So what the stream was the control room, and it was basically NASA's regular stream for landings. So we decided to design a solution where basically NASA and AWS would build their own live stream solution, just using EC2. So there are some constraints, right? So the maximum connections to each origin server were only 6. There's also a max of 20 streams per cache node, so you need a lot of cache nodes. And latency was critical. This was going to be a global event. People were going to be watching it all over the world, so you couldn't serve all the traffic from one endpoint, in some geographic location. So the plan was to build this solution around these constraints and test it and hope it works. So again, it was only 2 guys from NASA that could work on this. Now, luckily, one of them was a rocket scientist, so that helped a lot. And so here's the general architecture. So somebody at JPL had a MacBook Pro with a Telestream server on it, and that would beam the video out to 2 Adobe Flash Media servers. And so they would then send the video out to several Tier 1 cache servers, and then they'd also send it out through CloudFront, but only to museums and places where they had big viewing parties. But the tier 1 cache wasn't enough to support the capacity they needed. So they had a tier 2 cache, and each of these tiers, the tier 2 cache was an auto-scale group of Nginx. And then in front of that, they had elastic load balancers. And then this was all deployed in the form of a CloudFormation stack. So if you're unfamiliar with CloudFormation, basically it's a JSON file that just that defines your architecture. So you could say, like, I want a load balancer, and I want an auto-scale group with these images, and I want a CDN in front of them. So you could basically just define your whole architecture, your whole stack in a file, and then you could deploy off that file. So what their plan was to basically just keep launching stacks. So each stack was going to be about 25 gigabits of capacity. So they were just going to keep launching more and more stacks to maintain enough capacity. So the first thing, to test that the assumptions were right and everything, we used Swasta to load test this. So as you can see on the screenshot, we pointed 10 million users to the manifest file. And so as you can see on the chart there, it hit about 25 gigabits, and it worked. And then it hit about 27, and then things started airing out. So that was actually good. We tested, our assumptions were correct. And so this is a chart of the actual traffic data on one of these CloudFormation stacks, right? So we had 40 nodes, basically, M2 2x large instances, and it worked at exactly 25.3 gigabits a second. So, and then we had to test that the origin worked, that it was actually caching and not pulling everything from the origin. And so, as you can see, it was only actually pulling 42 megabits a second from the origin. And so, we did all this stuff, and it worked, right? And not only did our streaming work, but the rover landed without crashing. So, great success. And so what did they learn? So the first thing was that testing is essential, right? So we basically tested to as much capacity as we thought, or as much traffic as we thought we were going to receive. So when it came time to the actual event, there's a lot of confidence because this had all been tested. It wasn't theoretical. CloudFormation made it a lot easier to do this, right? So we didn't have to deploy each stack separately. We just literally had a button, it had the CloudFormation file, and the NASA folks could just run another stack and click the button and watch it spin up. And so that made it really easy. Now, the other thing is you really have to test everything in your stack, and it's always something that you don't expect that breaks. So, the actual live stream was solid, it was tested, but the web page with the live stream on it was running on a CMS. That CMS was running, off of a database. That database we discovered really, close to the actual landing was the database was really undersized. So we had to make it about 16 times bigger. And so it's good that we caught that beforehand. So and another interesting story was that the actual pictures off the rover, they're stored in S3 among other places. And so this was the first picture that that came off the rover after it landed. It's only about 17 kilobytes, but this picture actually, all told, used up more bandwidth than the whole live stream. So sometimes it's about volume, not just the size of the files. And the great thing about this was because it was in S3, the video or this picture was put into S3. It kicked out a URL. That URL was put on a website, and it just worked. No tweaking, nothing. You just put it up there, and it works. And that's the beautiful thing about serving static assets out of S3. So now let's talk about the Obama campaign. So the biggest thing, one of the biggest things for a presidential campaign these days is to be able to raise money through donations, right? So all told, at the end, it was about the 30th biggest e-commerce operation globally. There were a lot of applications. There were about 200 full applications with full stacks, so app tier, web tier, database, about 200 of those. There's also a really big team of data analysts, and so these data analysts, there was about 50 of them, and they were going to run all kinds of experiments and all kinds of queries and stuff on hundreds of terabytes of data spread on thousands of instances, right? And the other thing is, since it's an incumbent presidential campaign, there's always the off chance on any given day that the president could be on TV and could mention a URL that you're working on, and all of a sudden you have thousands and hundreds of thousands of concurrent users. And so you have to be prepared for that, and all your systems have to scale for that, right? So now here's the not so fun part. Campaigns don't typically have a really high tech budget, so we basically couldn't spend a lot of money. All told, there's about a year to build all these systems, right? And most of the developers were either volunteers or near volunteers, by which I mean they took giant pay cuts to work there. And the other thing is that, how many of you have failed to deliver code on time sometimes, right? Probably most of you. So in order to push back election day, you need an act of Congress. So you really have to get this, everything has to work on election day. And that day, if it doesn't work, you fail. So this was the picture of the whole team. And it was about 40 developers and about 5 DevOps people. And this was probably, the best group of people I've ever worked with. Very hardworking and dedicated, and some of the smartest people I've worked with. So a lot of us grew beards, like victory beards. There's Harper, he's the CTO there. I'm in there, I think my beard's about the least impressive. And so, it was a lot of fun. And this is what it looked like generally at the campaign office. So it's like your typical startup, except it's probably smelled a little funkier. There's bottles of beer everywhere and Nerf guns and caffeinated products. And people slept under their desks. So it was a cool experience. This is a picture from election day. So we had some high-profile help at times. So there's Eric Schmidt up there, and that's Harper, the CTO, with all the way in the back. And he also had a fridge of cheese, right? So it's kind of interesting. So what did we build? All kinds of stuff. We had websites. We had communication tools. We had to target our advertising both online and TV. We had all kinds of analytics tools, big data warehousing appliances, iPhone apps. We had reporting for our leadership. We had to do a lot of voter registration online. We also had a lot of volunteers, like thousands of volunteers that we had to coordinate. So this is just an example of some of the systems that we had. So there's a call tool up there, and so what that did was it would pull down a universe of callers, right? And then it would give you a script and tell you who to call, and then you would put in input as to whether the person was favorable to your call or whether it's a wrong number. And that data would then automatically get sent back to the proper databases and available to data analysts to update their universes and work off that data. One of the most important systems we had was a payment processor, so we could take online donations. Now, traditionally, campaigns have relied on vendors for this sort of thing, but we decided we needed this to be scalable, and so we built our own. And it was multi-availability zone, obviously, but also multi-region. I'll tell you a little story about it later. And so over the course of the campaign, we raised over $1 billion, right? Most of it online. We also had a thing called Dashboard, and that was like a social network for the campaign. And so community or the field organizers could talk to their teams, and team members could talk to each other, and you could see what events were going on. You can make calls, all kinds of cool stuff. And we had a canvassing app. And so that would tell you, go knock on these people's doors and go tell them this, and then the input from that would, again, go back into the proper databases. And we had voter registration tools, all kinds of stuff. And so we built all of it, and it worked. And then we won, and it was awesome. So what are the challenges with that? So this is our typical chart of our traffic. And so this is about from July to election day. And that little last block there is the last week. And so basically all of our traffic charts look like this. And what this traffic chart really is just a world of pain, right? So you have to be able to scale to that. And here's another, this is Scott, the head DevOps engineer on the campaign. And so he just posted, after the campaign, he posted some scary statistics. Again, world of pain. So how do we do this? So traditionally what people have done is, you go to Amazon.com and you buy a server and you can get it on Amazon Prime and it'll be delivered by Thursday. Now, we would have had to do something like this, and the campaign headquarters doesn't really have great colo space. There's a closet somewhere and there's a leak in the closet, and we might need it before Thursday. So this wasn't going to scale. So we looked at all the options right at the beginning of the campaign, and we decided that cloud computing was perfect for us. We didn't want to have any upfront capital expenses. At the very beginning of a campaign, you have almost no funds. This is before all the fundraising is going on, so you can't be buying a bunch of servers. You want to pay for exactly what you use, because then at the beginning of the campaign, you're building stuff, but you're not really using that much resources, so your bills are going to be low. You also want to be able to deploy stuff yourself. So you want to hit a button, you want to get instances popping up, and so that's really important. And you want to be able to scale up, but also to scale down. Scaling down is really important, both to control costs, but also, just to give you a frame of reference, at the 2008 campaign, it took months after the campaign was over to get rid of all the equipment, right? And this campaign, the day after election day, our infrastructure went from over 1,000 instances to, maybe 100 without, much work. So here's our, just a big picture of our infrastructure. So that's a live website that you can go to, and you can zoom in on it, and you can see which technologies we used, and it's a pretty cool site. So let's talk about some things in detail, right? So we had to have, one of the things we had to have was all these web scale applications. So www.barackobama.com was a CMS powered by MySQL. So what we did was we had a CDN in front of an auto-scale group that was across multiple availability zones, and it would grow and shrink based on CPU load, and then it had a multi-availability zone RDS instance, so RDS is just hosted MySQL, and that's how we made that work. And then the payment processor was another auto-scale group, just a web app with a database behind it, and that one we actually had on the East Coast and on the West Coast region, and we just used a weighted round robin to distribute traffic across the regions. So we also had to have some really big database systems. So we had this, this was before Redshift came out, so we had to buy a vertical license, and we had a vertical cluster that was on AWS, and then we had one on-prem. So the one on AWS, it used provisioned IOPS. It had a bunch of volumes, basically RAID 0 together to get really good IOP performance. And then I believe we used the cluster compute instances, so you get the 10 gigabit bidirectional communication between them on the network. And then we also had Dynamo for a bunch of stuff. We had an app called People Match. So what that would do is it would talk to Facebook's APIs, and it would then basically pull your friends list if you allowed it to, and it would then compare the data from your friends list to our voter file databases that we had at the campaign of the DNC, and it would figure out which of your friends haven't voted yet, or earlier than that, which of your friends haven't registered to vote yet. And so if they haven't registered to vote, it would send you an email saying, hey, you should tell these people on your Facebook page to go vote. And it's actually a lot more effective to do that than for us to send the person an email, because then it's a friend telling someone that. So anyway, this was hosted in Dynamo. This specific database had 400,000 write capacity units, so it really had to scale. Now, we also had basically an API that covered the whole data tier. So it's called Narwhal. There's been some articles about it. So what Narwhal was traditionally campaigns have had this problem of having different silos of data. So the digital team would have their own database, and the data analysts would have their own database, and then the field organizers would have their own database, and they wouldn't talk to each other. And so as a result, people would get called a million times, and you'd have frustrated voters, and all kinds of things go wrong. So this was an API that talked and had integrations with all these different databases and presented it as just one data set to all of the apps that the campaign wrote. So when a developer had to write an app, they didn't have to worry about any of this stuff. They could just talk to this API and pull out a voter, and a voter could be, it was the same person. So you could have the same person be a voter in one app, and you could have that person, check their voter registration status, and you could have them be a volunteer. So it made things a lot easier. So what do we use? We used basically everything in existence. So, when we hired engineers, we didn't look for any. We looked for their talent. We didn't look for any specific, language. So whatever they came in with, and they were comfortable with coding things in, that's what they would code things in. And so we had apps where one tier was one language, another tier was another language. So same thing with data stores. We used Dynamo, we used MySQL, we used RDS, we used Mongo, really everything, right? And it just really depended on what the app was and what it needed. And we found that to be a lot more flexible and easier than just saying, oh, well, everything's going to be MySQL. So same thing with development frameworks. Like I said, we'd have an app where the front end was in PHP and the app tier was in Python, right? And the iPhone app was in Objective-C. So a developer would come in and they'd just start working with the skills they already had. For infrastructure and monitoring, we use Boto a lot. So Boto is a Python library that you can use to automate talking to the AWS APIs. We used New Relic for application monitoring. So we had Cloud Init to bootstrap things. We also used Puppet. So we used the combination of Cloud Init and Puppet to bootstrap all of our instances when they came up in the auto-scale groups. So we made all these choices. In the beginning, we were kind of worried about the stuff in the gray area, right? So we thought, oh, we're going to be writing things in a million languages. It's going to make operations really complicated. And we have all these different databases, so that's going to lead to data corruption and fragility. And what we actually found out was none of this was true. So because we used all these different languages, we could build as little as possible. Like I said, we didn't have a lot of time. So if there was some pre-made system or framework that let us create things faster, that's what we used. The fact that we hosted it on AWS allowed us to run things at a scale we would have never been able to do on-premise given the time that we had, and also at a very low cost. And then for the databases, we just use the right tool for the right job. There's certain apps that need a NoSQL database. There's other apps that need a relational database, and so that's what we did. And using queues and SOA helped us a lot as well. So I'll tell you a story about that. But basically, all of our apps, or all the tiers of our apps, didn't talk directly to each other. They would talk through APIs, and they'd also talk through queues. And so just to give you a sense to talk more about the scale part. So in 2003, Amazon.com was a $5 billion business. It had a lot of employees, and it had a lot of servers. So last year, every day, AWS added enough capacity to just power this $5 billion enterprise every day. But SQS. So SQS is actually an interesting service because everyone talks about EC2 and S3, but not a lot of people know about SQS. It was the first Amazon Web Service, right? And from 2006 through 2008, it had a lot of customers, it had a lot of servers, and it had about over 5 billion queued events went through it. So during the campaign, OFA produced 8.4 billion queued events just on its own in the last month. And this required no sort of capacity planning. We just wrote apps that used SQS and threw them, through SQS messages up there, and everything just worked. And it was multi-availability zones. It was HA. It was beautiful. So now, for a lot of this stuff, we could have coded. We could have not used SQS. We could have just had our own queue software and run it on EC2. But there's one of the reasons that we didn't is because SQS is so much more economical. So SQS, you pay 1 cent per 10,000 requests. You pay 8 cents per hour for a small instance. And that's not even a fair comparison because for it to be scalable, right, you're going to have way more than one instance. So it's going to cost you a lot more. And like I said, we had no time to waste. Every time I'd come into the office every day and I'd see this countdown getting shorter and shorter. So that goes for a lot of this stuff. We ended up using a lot of partner tools, like I said, like Chartbeat or New Relic, right? And then we also used a bunch of the AWS services like ELB and Elasticache and Route 53 and S3. And we could have, had our own storage layer. We could have hosted our own DNS. We could have run HA proxy, like all the stuff we could have done by ourselves. But we had to ask ourselves, did we have a really good reason to do that? Because if you could build all this stuff, but like the slide says, do you have the extra focus, expertise, time, risk tolerance, and all this stuff to be able to do that? So instead of putting our best engineers on setting up our load balancers, we put them on our actual apps that differentiated our campaign from their Omni campaign. And just to give you an example, so we did use Mongo for some stuff, and we do have a Mongo white paper, and so you can launch Mongo in a CloudFormation script in an HA configuration in about 7 minutes on AWS. But it would be pretty hard to do this, right? So in 5 minutes. So we provisioned a Dynamo table, and we inserted 7.5 million records into it in 8 minutes. And that's really hard to do on your own. The other thing that's really hard to prepare for is natural disasters. So see right there, the center of it, that's Hurricane Sandy. And the center of it's right between Baltimore and Philly. And all of our stuff was in US East. And our on-prem data center was also in Northern Virginia. And so that's a little bit too close to the epicenter of the hurricane. So we were kind of scared. So we had to get all our stuff out to the west, right? So Scott, the head DevOps guy, bought us this cake. And the funny part about this cake was, we knew what it was for, right? But a lot of the developers and just other people that would walk by our desks would come and see this cake, and nobody would take a bite into the cake because they thought the message was about the cake. So finally, I think somebody took a piece of the cake, about 4 days after it was purchased. So it probably wasn't that good anymore because it had been sitting there. So we had been working the whole campaign to build this part of the infrastructure. So it was about 1,000 instances. It was maybe a little bit more than that. And so for the last 3 months or so before the hurricane, it pretty much looked like this with the auto scale groups and number of instances varying. So like I said, this was built using Puppet. So we'd have databases that were typically managed. We'd have auto scale groups. The auto scale groups, when the new instances would come up, they'd be provisioned by Puppet. It all worked really well. So we built the West Coast part of it, which was about 560 instances in 9 hours. So how do we do that? So Puppet's great, but sometimes it takes, if you've got a bunch of manifests, it'll take about 10 minutes to spin up an instance, right, or a little bit more. And so that's a long time, right? And especially if you're moving massive amounts of things. So what we did was we still used Puppet to build our template instances, and then we'd make AMI images out of them, and then we used Netflix's Asgard tool to actually deploy them. So when they'd come up on the West Coast, they would spin up immediately. They would do a Puppet run, but it wouldn't really do anything because it had already been configured. And so things would come up really fast, and then we used Boto to copy the security groups over. And we also, now the hardest part was actually moving over the data. We had an analytics database that was about 27 terabytes. And so moving that from east to west really fast was a challenge. But we got it working. I'll tell you how about the data part in a second. And so what we discovered was we could have cross-continent fault tolerance on demand. And that was awesome. If we wanted to, we could have also, we didn't have to go to the West Coast. We could have deployed in Singapore or Sydney or any of the other AWS regions really fast. So the other thing that was really necessary to do this was a lot of caffeine. So I wouldn't recommend that the energy shot, the inhaler, the green thing there, it's not very good. So how do we replicate the data? So for database replication, what we ended up doing for some of our databases was we used CloudOpt. So we had an SSL tunnel established between east and west, and it would use WAN optimization software to blast the data across. And then for just raw file transfers, this was we were transferring the backup for that analytics database. We used TsunamiUDP, which is a open source application. It's free. And so we discovered on a cluster compute CC2 8XL instance, we could transfer data at about 478 megabits a second. We also discovered, so actually the limiting capacity on Tsunami UDP is that it's single-threaded. So if you're on a big enough instance, you could just run multiple Tsunami UDP threads and get more bandwidth out of each instance. So this added up to about 1.2 terabytes an hour. We had 27 terabytes of data to move. So in 3 hours, we just split up the data among 4 instances, and we had it moved over to the West Coast. So what did we learn from all of this stuff, right? So the first thing is we learned to practice for failure, to know what failure looks like. So we had this thing called game day. So this was about 2 or 3 weeks before the election. We came in on a weekend, and the DevOps team started breaking all the infrastructure on staging. So we'd take a look at a security group and remove all the rules. So now the database couldn't talk to the app tier anymore. And we go to the developer and say, well, you can't see your database anymore. How are you going to make your app work, or at least fail gracefully? We detach EBS instances, we detach elastic IP addresses, all kinds of nasty stuff, just to see what would happen. And then we also had a small team that was documenting all this stuff and writing the playbook for when this sort of thing would happen for real. And so the other thing that we did was we had loose coupling. So we used SOA, and every tier of most of our apps just used SQS queues. And so just an example of how valuable this is, it was the vice presidential debate. So debates and conventions and high traffic events, especially for fundraising, because everybody's watching the debate. They see like Paul Ryan say something that they disagree with, and they want to, they get angry and they want to donate. So we were raising, several, $1 million in less than an hour, and all of a sudden our DBA on our DevOps team goes, oh hey, the database for your payment processor, it's at 95% CPU usage right now. It's about to fall over. We need to upsize it. Now, upsizing means a reboot, right? So that's going to be about 10 minutes of downtime, which isn't good, right? 10 minutes of downtime when you're raising millions of dollars an hour is a lot of money that's lost. So luckily, the way our payment processor system worked was somebody would put in a payment. It would send it to an SQS queue. The SQS queue worker would then commit that payment to the database, right? So while we were rebooting the database, we didn't even tell the CTO we were doing this. We don't want to make him nervous. So while it was rebooting, the queue just added up a little bit, and then it came back up. The workers cleared out the queue. Not one transaction lost, not one donation lost, and nobody noticed except us. So that was really cool. The other thing that we did was we had no rollback policy. So we'd have hundreds of deploys a day between all of our apps, and we just deployed all the time, and it was little iterative steps. And so if something got messed up, it probably wasn't a big thing, and we would just iterate again. And the other thing is, you still know that you can break something pretty badly when there's no rollback, so it made our developers a lot more disciplined. And developers also, the other thing that we did was all the developers got the same alerts that we did for all the apps they were responsible for. So they knew if their app was down, and they knew exactly why it was down. It also made them feel more responsible for what they were working on. Now, the other thing is you have to build in HA into every single tier of your infrastructure. So a really easy thing to do is to decouple all the static elements of your sites and put them on S3. And then you can put Cloudflare in front of that, and it's solid. So you can use Jekyll to use it as a CMS for managing your static content. And so we had a ton of, just aside from the static elements of our dynamic sites, we also just had a bunch of sites that were just purely static. And so most of these sites, we'd release like 2 of them a week, and like nobody would go to most of them, right? And so I remember one morning, or one night actually, they told me, hey, you should set up RomneyTaxPlan.com. So I go register the domain, I go set up the IAM policy and send it to the front end person, and so I don't think about it. I've done this a million times before. It takes me about 30 minutes, and then so I go to sleep after that. And then I wake up the next morning. I'm on the train to work, right? And I read Reddit on my phone, and I see that it's the #1 page on Reddit. So, and then at the same time I notice, I'm not getting any alerts on my phone. is email down, or is it, this is great, why is everything working? And then because it was on S3 and it had a CDN in front of it. So this particular site was #1 Reddit. It had over 17,000 concurrent visitors on it, and it just worked. Just not, there wasn't even any sign of trouble. So after the campaign, there were a bunch of startups that started as a result of the campaign. So the campaign transformed into Organizing for Action, which is a super PAC. And they still own most of the source code and most of the data that was developed. Then there's all these other startups, a lot of data analytics startups. There's a startup Circle that's basically a social e-commerce site. There's also Palomino, which is a DBA company, which is great. They write a lot of our white papers for Mongo and Postgres. And also just political strategy companies, right? So what should you do next? If you want to work on really cool projects, we're hiring, so you should come talk to me after the talk. So I'm a solutions architect, so what I do is I have a broad range of customers that I talk to, and I make sure that they're well architected. I help them with their really challenging problems and projects, and it's a really fun job. And then the other thing is you can look at some of the campaign source code. So they've released their voter registration tool, so it's on GitHub at Democrats. /voter registration, and so you can get your own voter registration website up and running pretty fast. It's written in Ruby on Rails. And then also Dylan Richard, who is the director of engineering at the campaign. He was one of the guys with a really long beard. In fact, I think he had the longest beard. He wrote a book on game day. And we're also going to have our yearly conference, which last year was the first one in Vegas, November 12th through 15th. So you should go and register for that. We're going to have a game day there, so what we're going to do is have 2 teams, right, of developers. So we're going to teach a 4-hour architecture course. Then after the architecture course, you're going to build a batch processing stack on AWS, and then you're going to hand over your credentials to the other team. And they're going to break your architecture really badly as they can, and then they give you back the creds, and you have to figure out, how do I fix this? How do I make this automated so I can just rebuild it really fast? And so last year at reInvent, Netflix was there, Pinterest was there, a lot of awesome, really interesting people were there, so I highly recommend you go there. So I'm LeoZH on Twitter. If you have questions, you can email me, Leo at Amazon. And like I said, we're hiring, and those are URLs, which you can't see very well, for more on what we did at OFA and NASA. And so I'm sure these slides are going to be published online, so you can see them there. Thank you.